In this lecture, we are going to study the tracking problem when the sensor has its own dynamics. Depends on the type of dynamics of the sensor. If the sensor is just a gain, then we can transform the non-unity feedback into the unity feedback. But when the dynamic of the sensor is not just the gain, then we cannot transform the feedback system into a unity feedback. Then we will study, in this case, how do we define the type of the system and the steady state tracking error. First, let's find the transfer function from the input to the output. Based on the block diagram algebra, we know the transfer function from the input to the output. The numerator will be the forward path gain. That will be ds times gs. Here, let's assume W is 0 and V is 0. The case that without any disturbances and sensing noises is 1. The denominator will be 1 minus the loop gain. Only one loop is 1 minus negative dgh, is 1 plus dgh. Here is the transfer function. Then we can calculate the error signal, the input, the difference between the input and the output. It will be Rs minus Ys. So Ys is Ts times Rs. So Rs minus Ts, Rs. Then we can obtain the transfer function from the reference input to the error. You have to pay attention that when it is not unity feedback. So here, it is not the ES. So here it is Rs minus HS Ys. It is different from the error. Yes, they're not the same. Then the reference to the tracking error transfer function will be ES over RS will be 1 minus T. So we divide RS on both sides. We have E minus TS. Then we have ES is 1 minus TS RS. To study the steady state tracking error, we can use the final value theorem. But the basic assumption how to assume closed loop system is stable. Without the stability assumption, we cannot study any tracking. If we use the final value theorem, it should be the steady state of the tracking error is Et. When t goes to infinity, it will be s go to 0, s times the Laplace transform of Et. So Et is 1 minus Ts Rs. So have s 1 minus Ts Rs. Let's still use the polynomial input. So if a polynomial of degree k, then we know the Laplace transform of Rs is 1 over s power of k plus 1. Then Es, it will be 1 minus Ts, 1 over s power of k plus 1. Then we plug in Es into the final value theorem. Then the steady state tracking error will be S is from the final value theorem. So Es, we have the transfer function, then the Laplace transform of the input. So S is cancelled by 1. We have 1 minus Ts over Sk. Similarly, let's consider the step response. When it is step response, it's a polynomial of degree 0. This means k is 0. Then we have s power of 0 is 1. 1 minus Ts will be 1 minus T0. Then we know if the system is stable, it can track a step signal with tracking error 1 minus T0. Then for here, we know the DC gain for type 0 system. The DC gain may not equal to 1. If it equals 1, the tracking error is 0. But if it not, the tracking error is now 0 for type 0 system. Now let's consider type 1 system. For type 1 system, the reference input is a polynomial degree of 1. So we have, so k is 1. It's a ramp signal. S1 minus Ts. Then if the system is a type 1 system, so 1 minus Ts must contains S Otherwise, the tracking error will be infinity. Must can be written in some form in this way. Then S is cancelled. T1, 0 is different from 0. So this is the type 1 system. So in this case, we must have the T0 is 1. The DC gain of the closed loop system is 1. Similarly for type 2 system. Type 2 system can track parabolic input, that's degree of 2, k is 2. When k is 2, have 1 minus ts over s squared. So in this case, 1 minus ts must contain a square. Then a square is cancelled. Have T2s, then T2, 0 is not 0. Then the system is a type 2 system. So in this case, we must have 1 T0 is 0. This means T0 is 1. This means the DC gain of the closed loop system is 1. Then we define system type K if the steady state tracking error is a non-zero constant when the input is a polynomial of degree k. Then for system type 1 or higher, the system must have a closed loop DC gain of 1.